You know, there's this line I came across, and it just feels like the perfect way to start this.
Oh, yeah. What's that?
We have loved the stars too fondly to be fearful of the night.
That's beautiful. And it really captures the spirit of what we're trying to do in this deep dive. We're using the sources you sent over to look at travels in space and time and really explore how the cosmos connects everything, space, time, and, human ambition.
And we're going to start this entire journey in a place that feels, well, really down to earth, the beach.
The beach is the perfect starting point. When you're standing there and you see the surf coming in and out, that's gravity. That's the moon and the sun pulling on the earth from an incredible distance.
It's an invisible force acting across empty space.
Exactly.
Yeah.
And then you look down at the sand itself. I mean, those tiny grains, they're the result of eons of erosion, rocks being worn down by those very same tides. It's a reminder that the world is just so much older than we are.
Okay, so let's get into the first big aha moment, because the scale is just staggering. If you were to reach down and just scoop up one handful of sand, you'd be holding around 10,000 grains.
10,000.
And that number, just one handful, is already more than the number of stars you can see with your own eyes on a perfectly clear night.
Which is such a powerful thought. It just immediately shows you how limited our perspective really is. And if you think that number, 10,000, feels big.
Well, the cosmic counterpoint is that the total number of stars in the universe is greater than all the grains of sand on all the beaches of Earth.
On all the beaches, all the deserts, everything.
Everything. The cosmos just dwarfs our world.
I think we're all feeling that initial shock of scale right now. So that sets our mission for this deep dive. We have to move from these tiny grains of sand right up to the very edge of physics, to the speed of light, and figure out how we could ever reach the stars.
And to do that, the first thing you have to accept is that the constellations we all know, they're an illusion.
Completely arbitrary. Completely. They're just random groupings. You have some dim stars that look bright just because they're close, mixed in with genuinely bright stars that are incredibly far away. Our ancestors just, played connect the dots.
And it doesn't matter where you are on Earth, right? Boston, Beijing, the pattern looks the same because the stars are just so far away. So how far would you have to travel to actually see those patterns break apart?
You'd have to travel distances that are comparable to the distances between the stars themselves. We're talking light years. And just as a reminder, a single light year is 10 trillion kilometers.
Yeah.
It's a mind-boggling distance.
And we can actually see this happen, right? We have computer simulations that let us travel that far. You can, fly 150 light years away and look back at the Big Dipper?
Exactly. And when you do, that familiar shape is just gone. It's completely distorted. You'd be seeing star patterns that no human has ever laid eyes on.
What's really fascinating, though, is that they don't just change when you move through space. They also change over time.
Right. Because stars aren't fixed. They move. They're born. They die. Sometimes they explode. The night sky is always subtly in motion.
So if we use those same computers to go back in time, say, 1,000,000 years, what did the Big Dipper look like then?
Back in the Middle Pleistocene, it looked quite a bit like a spear. You could almost use the constellations as this massive cosmic clock.
And if you go forward in time...
Even more dramatic. 1,000,000 years from now, Leo the lion will look even less like a lion. But the real show is Orion the hunter.
Ah, right, because the middle star in his sword isn't actually a star.
It's not a star at all. It's the Orion Nebula. It's this enormous cloud of gas and dust where new stars are being born, and these are massive, hot, young stars that live fast and die young. So a simulation of Orion in the far future would be this incredible display. Stars winking into existence and then exploding as supernovae, like cosmic fireflies.
It really gives you a sense of how fleeting everything is, even the stars.
And that fragility, that distance, it brings us right to the next big idea, the finite speed of light. Because light takes time to travel, looking out into space is literally looking back in time.
So let's start locally. Our sun is actually a bit unusual because it's alone. The closest star system to us, Alpha Centauri, is a triple system. But even that, the very closest star, is more than 4 light years away.
Right, and think about what that means. Let's take a star like Beta Andromedae,
Yeah.
which is 75 light years away. The light you see from it tonight, that light actually left the star 75 years ago.
So if it exploded, say, last week...
We wouldn't know about it for another 75 years. And just to put that in context, when that light started its journey, a young Albert Einstein had just published his special theory of relativity.
Wow. And the farther out you look, the more extreme this time delay gets. The center of our own galaxy, the Milky Way, is 30,000 light years away.
And the nearest major spiral galaxy to us, M31 in Andromeda, That's 2 million light years away. When the light we see tonight left that galaxy, there were no humans on Earth.
We're looking at a pre-human past.
Exactly. And when you get to the most remote objects we can see, the quasars, they're 8 to 10 billion light years away. We are seeing them as they were before our own galaxy, before the Earth had even fully formed. We are literally looking at the universe's baby pictures.
And that look-back time is crucial because it actually proves that galaxies evolve. We see more quasars the farther away we look, which means they were common events in the early universe, but not today.
So we have these immense distances, these unbelievable timescales, and we seem to be trapped by the speed of light. Our fastest probes, the Voyager spacecraft, are moving at 1/10,000th the speed of light. It would take them 40,000 years to reach the nearest star.
Which raises the big question, is interstellar travel just a fantasy? Or did Einstein, the man who set the speed limit, also give us a loophole?
And that takes us right back to that teenage high school dropout, Albert Einstein, in the 1890s. He's obsessed with this thought experiment, this Gedanken experiment.
What would the world look like if I could ride on a wave of light?
It's an incredible question. And it forced him to challenge common sense. I mean, Newtonian physics just assumed you could add streets together. If you're running on a moving train, your speed adds to the train's speed. Why not with light?
Because it leads to paradoxes. He realized that ideas we take for granted, like simultaneity, would break down. The old analogy of the bicycle and the horse-drawn cart moving near the speed of light.
Right. Could they have a near miss that seems simultaneous to the rider, but not to someone watching from the side of the road? Einstein realized the only way to make the laws of physics work for everyone, everywhere, is if the speed of light is constant for all observers, no matter how fast you're moving.
And that simple but revolutionary idea gives us the two great commandments of nature from special relativity. First,
Thou shalt not add thy speed to the speed of light. Its velocity is absolute.
and second, thou shalt not travel at or beyond the speed of light.
And this isn't just an engineering problem like breaking the sound barrier. This is a fundamental law of the universe. It comes from Einstein's rebellion against the idea of a privileged frame of reference. Relativity means the laws of nature are the same everywhere. For that to be true, the cosmic speed limit has to exist.
Speaking of speeds, it's funny how people talk about the speed of thought. It's not fast at all. Neural impulses travel at about the speed of a donkey cart.
A very slow donkey cart.
Yeah.
But the real genius of special relativity is that, while it puts up this absolute barrier, it also gives us a truly unexpected way around it. And that is time dilation.
Right, so let's try to visualize this. Imagine the speed of light wasn't 300,000 kilometers per second, but just say 40 kilometers per hour.
The speed of a motor scooter.
Exactly. As you get on your scooter and approach that speed, the world would start to look incredibly weird. Things behind you would appear in front of you, the world would squeeze into this tiny window right ahead of you, and your scooter would get heavier and heavier.
And while those visual effects are part of the thought experiment, the core physics is real. Time dilation is real. It's been confirmed again and again in experiments. Clocks on airplanes really do run slower. Particles and accelerators really do get more massive. For the traveler moving close to the speed of light, time itself slows down.
This is the elixir of life you mentioned. This is the loophole. The faster you go, the slower your personal clock ticks relative to the rest of the universe.
And that's how we could reach the stars. The traveler would age very little, while on Earth, decades, even centuries would pass. Special relativity, the theory that seemed to forbid star travel, is actually the only thing that makes it possible within a human lifetime.
So this moves the whole idea from science fiction into the realm of, well, a massive engineering challenge.
I think the Leonardo da Vinci analogy is perfect. He had these incredible designs for flying machines, but he was trapped in the 15th century. He didn't have a lightweight engine. Today, we have preliminary designs for starships. We're just waiting for our engine.
And we already have a couple of designs that could get us to the nearest stars. The first one was Project Orion back in the 60s. And this was, it was wild. It was basically a giant nuclear motorboat.
It really was. The idea was to detonate a series of small, controlled hydrogen bombs behind the ship, pushing it forward against a massive plate. And what's shocking is that it was considered entirely practical with the technology they had back then.
And it would have reached about 10% the speed of light. A trip to Alpha Centauri would take about 43 years.
But it was banned by the treaty that forbids detonating nuclear weapons in space.
Mm.
A real pity, in a way, for our interstellar ambitions.
Then there's the more recent design, Project Daedalus. That one requires a nuclear fusion reactor, which we don't have yet, but it's something scientists are confident will develop in the coming decades. But both of these are still relatively slow.
They're non-relativistic. To really harness time dilation, you need to get much, much closer to the speed of light. And for that, you need an engine on the scale of a small world. You need something like the Bussard Ramjet.
The Ramjet. This is where it gets truly incredible. The idea is to scoop up fuel as you go.
Exactly. The space between the stars isn't a perfect vacuum. There's about one hydrogen atom every 10 cubic centimeters. The Ramjet would have this enormous magnetic scoop, hundreds of kilometers across, to gather up that hydrogen and funnel it into a fusion engine.
The engineering is it's breathtaking. The magnetic fields would have to be strong enough to deflect all that incoming matter away from the crew.
But if you could build it, the payoff would be unbelievable. If the ship could accelerate continuously at 1G.
Which is the gravity we're used to right here on Earth, so it would be comfortable for the crew.
Perfect comfort. At a constant 1G acceleration, the journey times, from the traveler's point of view, become astonishingly short.
You could get to the Andromeda galaxy in just 28 years of ship time. You could circumnavigate the known universe in 56 years of your life.
And here is the devastating catch. The trade-off. While you've aged only 56 years on your trip around the universe, on Earth, tens of billions of years have passed. You'd return to find our sun long dead, the Earth a cinder. It's a one-way ticket.
That elixir of life is only for the person who takes the journey. It's such a powerful and lonely thought. And the lure of other worlds is strong. We think there could be 100 billion planetary systems just in our galaxy.
And we're actively searching for them. We can't see them directly yet, but we can look for the tiny gravitational wobble they induce in their parent stars. The nearest single star to us, Barnard's star, has been a prime target.
Have we found anything?
It's complicated. There have been a couple of studies that suggest 2 or 3 large Jupiter-sized planets might be there, but the data sets don't quite agree with each other. The observations are right at the edge of what we can detect, so we're still waiting for a definitive answer.
Speaking of different realities, that brings us to the puzzle of time travel to the past. Is it even possible?
Most physicists would say no, because of the logical paradoxes, the classic grandmother paradox where you prevent your own birth. But some speculate about the possibility of alternative realities, 2 equally valid histories existing side by side.
Which makes you wonder about history itself. Are there specific moments, these branch points, where one tiny event changes everything?
That's the key question. Take the poliovirus. It's a tiny organism, a millionth of a centimeter across. But it infected Franklin D. Roosevelt. Some argue that the suffering it caused gave him a deeper empathy, which might have fundamentally altered his leadership during World War II and changed the course of global history.
A tiny virus, a massive outcome.
But then you have other events that seem almost inevitable. If Queen Isabella hadn't funded Columbus, would history have changed that much? Probably not. The economic and technological pressures in Europe meant some other explorer would have made that voyage within decades. It wasn't a true branch point.
Which brings us to what might be the greatest branch point in human history. What if the scientific tradition of the ancient Ionian Greeks had never died out 2,500 years ago?
For that to have happened, their society would have needed to reject slavery, to embrace the dignity of craft, so that thinkers could also be builders.
If that had happened, we might have saved, 10 or 20 centuries? The insights of Leonardo or Einstein might have happened 1,000 years earlier, in that other version of Earth.
In that other history, or a different we might already be on our way to the stars, building fleets of starships inscribed with something like Starship Theodorus of the planet Earth.
It's the ultimate perspective check. Stars are born, they live, they die. Planets, people, civilizations, it's all the same cycle.
From the perspective of a star with a lifespan of billions of years, all of human history is just a tiny, instantaneous flash. We're like mayflies, fleeting, ephemeral creatures.
So what does all this mean for us right now? We're not ready for the stars yet, but we have the blueprints. Project Daedalus, the Bussard Ramjet.
Yeah.
They show us a possible path.
And we have to recognize that this moment, our time right now, is a historical branch point just as profound as the one the Ionians faced. The choices we make today about our planet, our technology, our society, they will absolutely determine the future of our descendants among the stars.
And that connection between the small choices of one generation and the grand trajectory of a species across the cosmos is a really powerful thought to leave you with. Keep looking up, keep exploring these ideas, and thank you for sharing the sources for this deep dive with us.